Welcome to this lecture series in number theory. In this lecture, we'll discuss a very interesting puzzle, and all we need is just the basic arithmetic of remainders that we have discussed so far, which is what we term as modular arithmetic. And I have beaten over it many times, so let me not spend any more time on it. Okay. Here are some problems for practice. And now let us get started. So what is the puzzle? There are 7 prisoners in a prison and a warden, and one day the warden decides to give the prisoners an opportunity to escape. So he will play a game with them. Here are the rules of the game. The warden will put hats on the heads of each prisoner, and each hat will carry a color, one of the 7 pre-decided colors. So there are 7 colors in the rainbow. Each hat will bear one of these 7 colors. It is possible that some color may repeat. In fact, it is also possible that all the hats have the same color. That is totally up to the warden. So we are not saying that the warden will distribute these colors in a one-to-one fashion. He may choose to use the same color as many times as he wants. But it is already known that the color palette is just this. He will not invent any new colors which the prisoners are not aware of. Okay, so this is what he will do, and then he will ask each prisoner, what is the color of the hat that he is wearing? So each prisoner is allowed to look at what the other prisoners are wearing. So he has access to the colors of the hats of all the other prisoners, but not his own hat. He cannot look at the color of his own hat. Okay. So the warden will go one by one and ask everyone to guess the color of the hat that they are wearing. So he will ask him, what color are you wearing? Then he will ask him, what color are you wearing? And so on. And the response of each prisoner will be heard by only the warden. No other prisoner is privy to the responses. Okay? And if at least one prisoner guesses his hat color correctly, the warden will set all of them free. But if no one is able to guess their hat color correctly, then all of them will be executed. So it's all or nothing game. And the prisoners are not allowed to communicate in any way possible. No eye gestures, no hand gestures, no funny business. However, the prisoners are allowed to strategize one day before. So they know the rules of the game. They are allowed to come up with a strategy among themselves that they may employ when the game is on. Once the game is on, they are not allowed to talk at all amongst each other, but they are allowed to strategize beforehand. Okay? So once again, the warden is completely free as to what color hat he will assign on what person, and each person would then be, and each person can look at the color of the hats of all the others but not himself, and based on whatever data he has gathered, he will guess the color of his own hat, and if at least one prisoner guesses it correctly, then all of them are set free, otherwise all of them are executed. Okay, and they are not allowed to communicate when the game is on, when the hats are placed. The prisoners are not allowed to communicate with amongst each other in any way. All right. So this is the puzzle, but I would also written it formally here if you somehow didn't follow what I was trying to explain. This is the formal way of stating it. Not a very formal way, but still semi-formal way. And it seems strange that such a thing is even possible. I mean, the question is it possible? But let me disclose it to you. It is possible to come up with such a strategy. The point is to come up with such a strategy. That is I've asked it in a way that suggests that there may be no such strategy possibly. But let me make your life simpler and tell you that there is such a strategy. You just have to find it. And it may seem very strange. No prisoner is privy to their own hat colors. Still, it is possible for at least one of them to guess their hat color correctly. It's very strange. But okay, so I encourage you to pause the video and try to solve this puzzle for yourself. It's a very interesting puzzle. Okay, and now let us move to the solution that I want to present. So the case of 7 prisoners is of course pretty complicated. When faced with any complicated problem, we should try to come up with a simpler version of the problem which retains some of the difficulty of the original problem. So the most natural way of simplifying or making the problem easy is to reduce the number of prisoners. The game remains the same. So this time we have 2 prisoners. I'm calling them Alice and Bob. There is a warden, which I'm not drawing, and he has challenged them with the same constraints. Of course, this time he can choose only from 2 colors. So let's say red and blue. So he might use a red colored hat and he might use a blue colored hat. And again, he would place some color hat on Alice's head, some color hat on Bob's head. Alice can see Bob's hat, Bob can see Alice's hat, and then each of them will be asked to guess the color of the hat they are wearing, even though they cannot see their own hats. They cannot communicate in any other way. And if at least one of them guess correctly, both of them are free, otherwise both of them are doomed. So that is the simpler problem. And as I said, they are allowed to strategize in advance. Before the hats are placed on their heads, they are allowed to discuss a strategy amongst themselves. And the question for now is, what is a strategy? Right? How do we even mathematically capture a strategy? So, what is the warden allowed to do? The warden is allowed to choose any element of this set. What is this set? This is basically the Cartesian product of this with itself. So this is a 4-element set with elements red, then another element red-blue, then another element blue-red, and then another element blue-blue. So this is what the warden can choose from. Once he chooses an element here, suppose he chooses an element here and it is, let's say, this ordered pair, red, red. Then what does that mean? That means that he will put a red colored hat on Alice's head and a red colored hat on Bob's head. Okay. And then Alice is allowed to look at this color. What Alice sees is the second color, because she's allowed to see what is there on Bob's head. And Bob will see this color because Bob is allowed to see what is there on Alice's head. Right? So a strategy is a pair of functions. Let me call them script A and script B, where script A is a function from the color set to the color set, and same for B. That is a strategy. It may look like a nonsensical thing, but let me explain why am I calling that thing a strategy. So once the hats are placed, Alice will see one of the colors. She will either see red or blue on Bob's head. And once she sees a color, she will, according to the rule, according to this function, she will just output what that function says. Similarly for Bob. So this is the rule by which they utter their responses. Right? So once you've chosen this function, now the warden comes, puts some hats here. Let's say he puts blue here and blue here, and both hats feature blue. Then Alice's response is A of blue, and Bob's response is B of blue. Now, whether they will succeed is a different question. This is a strategy, all right. This may not be a winning strategy. This may not be a strategy that saves them. For instance, you can choose the strategy as just answer red. No matter what happens, just A takes the whatever A consumes, it just answers red, and whatever the function B consumes, it just answers red. So no matter what the warden does, even if the warden puts both hats as blue, Alice and Bob both will be answering red, and therefore no one is answering correctly, and hence both of them will be executed. So that is a bad strategy, but that is a strategy. And as you can see, there are only finitely many strategies. In fact, there are only 16 possible strategies. There are only 16 such possible pairs of functions. And if you iterate over all of them, you will eventually land on a winning strategy, meaning a strategy which guarantees the survival of both Alice and Bob. So if you were stumped by the original prisoner's question, the 7 prisoner problem, you can pause the video now and think about what could be a solution. Think about a strategy that will save both Alice and Bob, no matter how devious the warden is. Even if the warden knows their strategy, the warden will be helpless. That is the power of a winning strategy. Okay, so let's solve this. Let's solve this this question. So instead of the colors red and blue, it is much more convenient to use the symbols 0 and 1. So the warden will decorate the hats with one of 2 possible symbols. Either he will write a 0 on a hat or 1 on a hat. That is his discretion. And here is the strategy. The strategy is Alice will utter what she sees. So what is Alice's guess for her hat? She looks at Bob's hat. Whatever is the color of Bob's hat, that is her guess for her hat. And what is Bob's guess? Bob will utter the flip of what he sees. I'll explain what I mean by this. So let's look at how the strategy performs in all the possible scenarios. So if the warden decorates the hats in this fashion, Alice gets a 0, Bob gets a 0. Alice sees 0, and what is Alice's response? Alice will just utter what she sees. So she will just say 0. And what will Bob say? Bob sees a 0, but Bob utters the flip of what he sees. He's seeing a 0, but what is the flip of 0? Think of 0 and 1 as coins maybe. The flip of 0 is 1. So Bob will utter 1. Fine, that's what they respond. But do they survive? Yes, they do. Alice has correctly guessed her hat color. Bob has not, but we were only required to have at least one correct response. So Alice has survived. I mean, both have survived. Alice has guessed correctly, so both have survived. So here they survive. What about this scenario? Alice sees a 1, so she'll just answer 1. Bob sees a 0, and he will flip it, so he will also answer 1. But this time, Alice has answered incorrectly. However, Bob has guessed correctly, so they survive. Next one, here Alice sees a 0. She will answer 0. Bob sees a 1. He will flip it, so he will also answer 0. Again, Alice has incorrect guess, but Bob has guessed correctly, so both of them survive. Lastly, Alice sees a 1. She will answer 1. Bob sees a 1. He will flip it and answer 0. This time Alice has guessed correctly, and Bob has not, but both of them survive. So this is a winning strategy. This strategy guarantees the survival of both of them, right? Maybe stay on it if it is unclear. But it's very simple. Let's review this. Let's review this in a sort of a different light. The same strategy I will express in a slightly different way. So here is what we will do. Suppose the color on Alice's head is A and on Bob's head is B, and again A and B are from 0, 1. The colors were replaced by numbers. So there are two possibilities. Either A plus B is congruent to 0 mod 2, or A plus B is congruent to 1 mod 2. We will devise a strategy which will make Alice win or Alice guess correctly in this path, in this case, and Bob guess correctly in this case. How can we devise such a strategy? What could that strategy possibly be, if at all such a strategy exists, which makes Alice guess correctly in this and Bob guess correctly in that? Now, in this situation, what is Alice seeing? Alice is seeing B. That's what Alice sees. And that is the only thing she can use to make a guess. A is not available to her. She does not know what A is. She only knows what B is. So if Alice were to guess correctly, she has to answer A. But she has only available B. However, can we express A in terms of B in this setting? Yes, of course. If A plus B is congruent to 0 modulo 2, then A is congruent to B modulo 2. So this is same as, so note that A plus B congruent to 0 modulo 2 implies or is equivalent to A is congruent to B modulo 2. Because, if you really want to be very, very precise or very, very pedantic, this says that A is congruent to minus B modulo 2, because you kind of take the B to the other side. But minus B is same as plus B modulo 2. We are working modulo 2, so B and minus B are the same. So what will Alice answer? Alice will answer just B. That's Alice's response. Right? So that will make Alice guess correctly in this path. And here we are trying to make Bob guess correctly. What should Bob be answering? Bob should be answering B. But he has only available to him A. Can we express B in terms of A? Yes, we can, because A plus B congruent to 1 modulo 2 implies B is congruent to 1 plus A modulo 2. So Bob has A available to him. His answer should be B. So therefore his answer should be 1 plus A modulo 2, which is as good as flipping. 1 plus A modulo 2 is precisely flipping the thing. Right? If A is equal to 0, what is 1 plus A? 1 plus A modulo 2 is 1. So you have flipped it. If A is equal to 1, what is 1 plus A? 1 plus A is 2. But 2 modulo 2 is 0. If you are to remain in the set of the colors, modulo 2 you will be answering 0, because 2 is not a color. Only 0 and 1s are colors. Modulo 2, your answer is 0. So that is as good as flipping. So in this case, so Bob will answer 1 plus A. But the strategy has to be consistent. Alice and Bob don't know the value of A plus B. So this is the strategy. Alice will answer B. Bob will answer A plus 1 modulo 2, of course. And that is exactly what the strategy was in the previous page. Alice was answering what she sees. Bob was answering the flip of what he sees. Okay, I hope so much is clear, and let's proceed. We haven't still solved the rainbow hat puzzle, the full thing. So let's increase the difficulty by 1 notch. This time we have 3 people, 3 prisoners, Alice, Bob and Chuck. Can we devise a strategy which makes all 3 of them survive? And again, here this time we have 3 colors, which we will think of as numbers 0, 1 and 2. So the warden is free to assign whatever numbers he wants He could assign 2 here, 1 here, 1 here, whatever, but of course, he can choose only from these. And we have to come up with a strategy which makes all three of them survive. Alice can look at the colors of Bob and Chuck. Bob can look at the colors of Alice and Chuck. And give me 1 second. This is better. So Alice can look at Bob and Chuck's color. Bob can look at Alice and Chuck's color. And Chuck can look at Alice and Bob's color. Right? And we will adapt what we just learned on the previous page. What we will try to do is come up with a strategy which makes Alice win if A plus B plus C is congruent to 0 modulo 3. We will try to make Bob win, and when I say win, I mean guess correctly, when A plus B plus C is congruent to 1 modulo 3. And we'll try to make Chuck guess correctly if this happens. So that's the kind of strategy that we are trying to devise. Okay, but again, Alice only gets to see B and C. Yeah. So let me write, just give me 1 second. Yeah. So let me write A, B, and C on their heads, otherwise things may get confusing. So these are the colors of their hats. What is Alice seeing? Alice is seeing that B is there on Bob's head and C is there on Chuck's head. To make Alice guess correctly, Alice should answer A. Right? Alice should answer A, but she sees only B and C. However, in this case, if Alice were to answer A, what is the answer Alice should give? In terms of B and C, she should answer minus B plus C, but modulo 3. So for example, if suppose there were the 2 written over here and 2 written over here, our answer should be minus 2 plus 2, which is minus 4, but modulo 3, this is same as 2. So her answer would be 2. Right? So if this happens, Alice's answer would be correct. Alice would have been answering the correct color of her hat. She may answer incorrectly if this is not happening, but at least in this branch, Alice is answering correctly. So this is Alice's response. Let me write that this is Alice's response. Similarly, here we are trying to make Bob guess correctly. Bob should be guessing B, but he has access to A and C. Can we express B in terms of A and C? Yes, we can. B is nothing but that. And here we are trying to make Chuck guess correctly. Chuck should be answering C, but he can only answer in terms of A and B. And long story short, Chuck's answer is, right, Chuck should be answering C, but he can answer in terms of A and B. So that's his answer, and that is correct if this holds. But one of these three should hold. A plus B plus C is some integer. It has to be either 0 or 1 or 2 modulo 3. If this happens, Alice is answering correctly. If that happens, Bob is answering correctly. If that happens, Chuck is answering correctly. So at least one is going to be answering correctly. Maybe let's just quickly see that in one example. So here, suppose the numbers were whatever, let's say 1, 2, and 2. What is Alice's response? 2 plus 2 is 4. Minus 4 is her response, which is modulo 3 equal to 2. So that is Alice's response, because 2 is, this is her response. What about Bob? Bob is answering 1 minus A plus C, which is congruent to 1 modulo 3. So 1 is Bob's response. What about Chuck? Chuck is answering 2 minus A plus B, which is congruent to 2 modulo 3, and yes, Chuck is answering correctly. Both Alice and Bob failed, but Chuck did not. Chuck saves the day. Chuck becomes Chuck Norris. Okay, so I hope this was clear. And now you can complete the solution for the rainbow problem. This is the solution for the rainbow problem. Don't read it. Write it down yourself. It's the same simple generalization of what we just learned. In fact, 7 is not a magic number. If there were n prisoners, you can still solve it. The same solution works. Alright, so I hope you enjoyed this puzzle. As usual, like, comment, share, subscribe, and I will see you next time.